Hello there, Mr. Sutton here, bringing you the AB Calculus 615 Extra Practice Number 2 solutions on integration with respect to the y-axis. On this calculator problem, I'm trying to find the area of the region enclosed by these curves. Let me go ahead and try graphing these out. So the first thing I'm going to do on my calculator is enter these in my y equals as 2x squared and 1 minus x. Now I know these are in terms of y, not x, but it turns out we can use this setup for quite a few things on this problem anyway. So let me go ahead and just graph those. So I'm basically graphing the inverses of these things. So everything's going to be flipped around above, what it normally is. Let me do zoom 4 on this. So the inverses of these things, we're basically going to flip both of these over the line y equals x. So I'm going to go back to my y equals now, and I'm going to deselect those. And what I'm going to do at this point, I'm going to quit out of there, and I'm going to use the draw menu. I'm going to do second draw, and I want to draw inverse, which is option 8. And I want to draw the inverse of each of those. Since I've already entered them as y1 and y2, I'm going to do draw inverse of alpha trace y1. Press enter, and that draws my sideways parabola. I'm going to quit out now, and let me yank my input from before. Draw inverse of alpha trace y2, and that draws my inverse line. So that's what I'm really looking at for this thing. So to find the area, I have to go I have to integrate from bottom to top, and I have to do right minus left function inside. So I need to find my limits of integration. I need to figure out where f of y equals g of y. I can do that on the calculator, but it's going to be a little tricky. So let me go back to my calculator, and I'm just going to clear that stuff out. Let me escape, and let me go to my draw menu again, and I'm just going to clear those drawings now. I don't want to see them ever again. What I am going to do is go back to my y equals, and now I'm actually going to graph those functions out as functions of x, and I'm going to find out where they intersect. So here they are again, and I've got two intersections, one over here, one over here. Now the x values where these things intersect correspond to the y values where the inverses intersect. So I'm going to find the x value intersections, and those will just give me the y values that I need to use over here. So let me do second trace, option 5, intersect. And let's move my spider over to the left one here. 1, 2, 3 enters. We have an intersection of x equals -1. So that means that these are going to intersect at y equals -1. That's the bottom intersection. And now to find the top intersection, let me do second trace, option 5 again. And we'll go over to the right side and press enter 1, 2, 3 times. That gives me an x value of 1/2, or 0.5. So that means that these functions intersect at the y value, 1/2. So in order to find that area then, I'm going to take the integral from -1 to 0.5, and these limits of integration are both y values now. And I need to do right minus left. So the rightmost function here is this line, which is going to be g of y. The left function is this sideways parabola, f of y. So I'm going to have g of y minus f of y dy. And on the calculator, how do I do that? So let me go back to the calculator. I'm going to do math 9 for integral. And I'm going to do -1 and 0.5 for my limits of integration, just like I have over here. Now in here, I'm going to use the functions that I stored in terms of x. And my calculator's not going to care because I'm going to write dx here. In terms, algebraically, those functions do everything these functions do. They just do it with an x instead of a y. So let me just do, let's see here. We need a g, so that's y2, alpha trace y2, minus, we're going to do alpha trace y1 to get the f function here. And by writing dx, I basically make my calculator do what we're doing over here. The only thing that needs to be true is these letters here, the y's, all need to match. So if I press enter, that gives me 1.125, and that is the area of that enclosed region. For this problem, I want to find the volume of the solid of revolution when the area between these curves is spun around the y-axis. So let me go ahead and graph these out on my grapher. So here I am in my y-equals. I've got both of those lines in there. And I don't need to graph x equals 0 because that's just the y-axis. So let me just do, I don't know, zoom 6. There we go. There's our first line. There's our second line. And I want this triangular region in here spun around the y-axis. All right, so there's a few things that come out of this. Since I'm integrating with respect to y, I am going to need to rewrite this formula here. So in order to do that, let me just, basically I'm going to solve for x. So if I subtract 4 from both sides and then multiply by negative 2, I'm going to have negative 2y plus 8 equals x. So that's step 1. I'm going to need to, express this in terms of y so that I have distances from the y-axis rather than distances from the x-axis. Next thing I need to do, since I'm getting a solid of revolution, I need to figure out what my cross-section area is. Am I using disks or washers? Well, this is the bounded region right here, and it's flush against the axis of revolution, the y-axis. So that means I can use disks here. So I'm going to write a of y equals pi r squared. The radius is just the distance from the axis of revolution. So that distance, that's just the distance from the y-axis to that slanted line, which we represented as x equals negative 2y plus 8. So that is just going to be negative 2y plus 8, that distance. So I can write pi times that stuff squared. And now I'm going to just be taking the integral from 2, the lower limit here, to the y value up here. Now what is that y value? Well, it looks like 4 to me, and I mean 4 is the y-intercept of the original line, so it is 4. But if you weren't sure, you could set negative 2y plus 8 equal to 0, subtract 8, divide by negative 2, and yes, indeed, y does equal 4. So my volume then is going to be the integral from 2 to 4, bottom to top, and then we have right minus left. So it's just going to be then, well, it's just going to be this area function actually. So a of y dy. And let me just do the rest of that on the calculator. Just to make this a little bit cleaner on the calculator, I'm going to enter my a of y function in my y equals, and I'm going to do it with x instead of y, and it'll actually work out in the end. So I've got, let's see here, pi times, open a parentheses, negative 2x plus 8, and close the parentheses and square that. So there's my a of y function expressed with an x instead of a y. Quitting out of there now, I'm going to do the integral, so math 9, and we're going from 2 to 4. In here, I stored that in y3, so let me do alpha trace y3. Now, since I defined this function in terms of x in y3, for my d here, I'm just going to put a dx. And really, as long as all these variables in here match up, it is just a dummy variable. Your calculator knows what to do as long as you're consistent with the variable. So pressing enter on that, we end up with 33.510, and that is our volume. For this problem, I want to find the solid of revolution when the area between f of y and g of y is revolved around the y-axis. So to start with, let me graph these out. To do this on the calculator is a little bit tricky, not as tricky as trying to do it without a calculator. But since these are in terms of y, what I'm going to do is my little trick here. I'm going to write them in my y equals in terms of x, and then I'm going to deselect both of them because I don't actually want to graph these ones. And I'm going to go ahead and use the draw menu to graph the inverse of these functions. So escaping there, let me do second program for the draw menu. And if I do option 8, draw inverse, I'm going to do alpha trace y1. This will give me the inverse of this first one here. So drawing that out, I see that I've got a sideways parabola. And now let me quit out of there and yank my input from before. And now I'm going to do draw inverse alpha trace y2. So this gives me this g of y equals y function here. So that's what I'm looking at. So, and I'm trying to find, let's see, I'm trying to take this area in here and revolve it around the y-axis. To find that volume, I'm going to have to find the limits of integration. So I'm basically going to be going from bottom to top because I'm integrating with respect to y. So let me do that first, and then I'll worry about the rest of it. So the limits of integration are going to be the y values where these functions are intersecting. I see that f of y and g of y are going to intersect. Well, let's see here. On the graph, it looks like they're intersecting at 0 and possibly 3 for y values. Let's test each of those out before I actually try to do this on the calculator. So let's see. If I plug in 0 for y, 4 times 0 minus 0 squared is 0. Plugging in 0 over here, I just get 0 back. So yeah, they do intersect at 0. And it also looks like they intersect at 3. Just to be sure, let me plug in 3 for y. So we have 4 times 3 minus 3 squared. That's 12 minus 9, which is 3. And if I plug 3 into the g function, I get 3 back. So yep, they also intersect at 3. Nice. Okay, so what am I integrating exactly? Well, I have, since this is a solid of revolution, I need to find the area of the cross-section, which is either going to be a disk or a washer, a pancake or a donut, and we're just going to add slices of those together with the integral. So because I have this gap between the bounded region and the axis of revolution, that tells me I need washers rather than disks. So my formula then for my area of my cross-section, I'm going to say a of y equals pi times big R squared minus little r squared. This is my washer formula. For big R squared, that's going to be the distance from the axis of revolution to the outer part of the function, and this is a left-right distance now. So that distance is expressed by this f function right here. This sideways parabola gives us that distance from the y-axis. So that's going to be f of y squared in there. And then little r squared, that's the distance from the axis of revolution to the closer part of the bounded region. That distance is actually given by the g function. So I'll do g of y squared. And at this point, I just have to do integral from 0 to 3 of a of y dy. Now I have to do that on the calculator. To make my life a little easier, make this a little cleaner on the calculator, I'm actually going to put this a of y function in my y3 of my y equals. So let me do, let's see here, pi times, and then open a parentheses now. We're going to do f of y squared minus g of y squared. Now to do that on my calculator, well, I have f of x basically up here. So I'm just going to do alpha trace y1. And I'm just going to use y1, and you'll see why this works in just a sec. Then I'm going to subtract, I need to subtract g of y squared. Actually, hold on, before I subtract, I need to actually square that function. So square it, there we go. Now I need to subtract g of y squared. So let me do alpha trace y2 and square that. Now, the reason this is going to work, even though these are functions of x instead of y, is when I actually take the integral on my calculator, I'm going to put dx instead of dy. So my calculator is just going to do exactly what this integral is doing, but it's going to use a dummy variable of x instead of a dummy variable of y. But mathematically, it is going to end up doing the same thing, believe it or not. So let's get out of here, and let me go to Math 9, integral from 0 to 3. And we're going to do alpha trace y3 now, because that's where I stored my a of y function. And again, I'm going to write an x in here because everything I did is in terms of x. Pressing enter, we get our answer of 67.858. And that's it for this one. For this calculator-based free response problem, R is the region enclosed by the graph of y equals radical x minus 1, and the vertical line x equals 10 and the x-axis. First task is to find the area of R. Well, my first task is to actually graph this and see what I'm looking at. So here I am in my y equals. There's my y function right there. And I'm going to graph this out now. So let me just do zoom 6. And actually, I don't need to see all of that. Let me go to my window and let me just start at -1 for the x values. Just kind of anticipating this vertical line I'm about to draw. Let me go to 12 for the x max. And this function doesn't really go all that high. So let me go from -1 on y values to, let's say, +4 on the y values. All right, so there's my new window. A little bit easier to see. And let me quit out of there now and do second program to get my draw menu. Draw a vertical line, option 4, and we'll draw that at 10. All right, so there's what I'm looking at. So that's the region R. And my first task is to find the area of this thing. Since I already have a function that's a y equals something in terms of x, I'm just going to integrate this left to right to find the area. So I'm going to be doing integral from, looks like, 1 to 10. And just to show that I'm getting my numbers from somewhere, let me find that first limit of integration by setting this thing equal to 0. So we can see that this does equal 0 if x equals 1. So I'm going to go from 1 to 10, and I'm going to be integrating basically top minus bottom. Now, since the bottom is just the x-axis, which is just y equals 0, my top minus bottom thing is really just going to be this square root of x minus 1 function. So I'm going to have the integral from 1 to 10 then of just radical x minus 1. So f of x here. Notice that I named this thing f of x just so I didn't have to keep referring to it over and over again as radical x minus 1. And now I'm just going to do this on the calculator. So on the calculator, let me just do math 9 for integral. We're going from 1 to 10. And I'm just doing f of x, so let me just do alpha trace y1, because that's where I stored this function I'm calling f of x. Let's do a dx here. Enter. And that is going to come out to, well, probably is exactly 18. This is just the calculator's kind of brute force approach to integrating. So let's just call this 18. For this part of the problem, they want to find the volume of the solid generated when R is revolved around the horizontal line y equals 3. So let me just draw that on this graph that I drew. So that's up there. So I have the same limits of integration going from 1 to 10, because that's the limits for R. However, this time around, I'm integrating area slices to get a volume. So those area slices, since I'm doing a volume with a solid of revolution, I'm either going to be dealing with pancakes or donuts, disks or washers. So to figure out which one, I look to see if there's a gap between the bounded area and the axis of revolution, and there is right in here. There's all this empty space. So that means I have to use washers for my cross-section. So I'm going to write a sub 1 of x equals pi times big R squared minus little r squared. And I'm writing a sub 1 because I'm going to be doing another area formula on the next part, so I don't want to mix it up with this one, so I'm just kind of thinking ahead a little bit. So now big R, that's going to be the distance between my axis of revolution and the outer part, the outer boundary of the curve, which happens to be the x-axis. So the distance between the axis of revolution and the x-axis is just a constant value of 3. So this is just going to be 3 squared, and I have this pi outside here still. Now little r squared, that's the distance from the axis of revolution to the inner part of the bounded region. This inner part is represented by, well, radical x minus 1, f of x basically, that I defined on part A of this problem. So I'm going to write little r as just 3 minus f of x. And I'm going to square all that and subtract it. So now my volume is just going to be the integral from 1 to 10 of a sub 1 of x dx. Now that I've written that and I've defined what a sub 1 really equals over here, I can just do all that on the calculator. To make doing this a little bit easier on the calculator, I'm actually going to take this pi and yank it outside the integral so I don't have to have another set of parentheses inside. And then let me do math 9 for integral. We're going from 1 to 10. And now I'm going to have 3 squared, which I'm not going to bother simplifying, minus, open a parentheses, we've got 3 minus the f function, which I stored as y1, so alpha trace y1 is how I'm going to get that. Close that parentheses and square it, and that gives us all the stuff inside this brackets there. Now let me just go over a little bit and put an x next to the d, press enter, hope for the best. And that volume comes out to 212.058. For the last part of this free response, the final boss battle, They want the volume of the solid generated when r is revolved around the vertical line x equals 10. So now we're basically integrating with respect to y, and pretty much everything has got to get flipped on its side. For one thing, I now need to rewrite this function here as x equals kind of thing, a function of y. I also need limits of integration that are now going from bottom to top using y values instead of left to right. So let me rewrite this function to start with, because everything kind of revolves around that, no pun intended. So basically isolating x, to do that I have to square both sides, so I have y squared equals x minus 1, and then I'll add 1 to both sides. So I can write x equals y squared plus 1, or if I want to be really fancy, f of y equals y squared plus 1. So now that I've named it f of y, I don't have to keep writing all this stuff. Now to find my limits of integration, again we're going from bottom to top. Lower limit is going to be y equals 0. It's just the x-axis, so that one's kind of a freebie. But up here we need to know what this y value is. It looks like 3, but let me set this equal to the x value 10 to see the y value at which those intersect. And if I plug 3 in here, or actually if I just solve, I mean subtract 1 square root, I am going to get positive 3 as one of my answers, and that's the only one that matters because that's what I see in the picture here. So y equals 3 then is going to be our upper limit of integration. So at this point I need to come up with a function that I'm integrating. Since I'm revolving again, I have to choose between disks and washers. Now this time around, the axis of revolution is one of the boundaries of the bounded region. My bounded region is flush against the axis of revolution. That means there's not going to be any space between the bounded region and the axis of revolution. So I can use disks this time around. So I'm going to write a sub 2 equals pi r squared. That's my disk formula. And this is a sub 2 of y now. This is a function of y. So I have to replace this r with something that has a y in it. Now the radius in this case is going to be the distance between my axis of revolution and this curve here, the other side of the bounded region, but this is a left-right distance now. So to get that left-right distance, I need to do the x value 10, which is my axis of revolution, 10 minus whatever x value this over here is. Now these x values are represented by this f of y function. When you plug a y value in, you get the x value out. So I can write this as pi times 10 minus f of y squared. And for my volume, all I have to do is take the integral from 0 to 3 of, well, a sub 2 of y dy. But now I need to do that on the calculator, and that's another task. To make this task a little bit more manageable, I'm going to do some work in my y equals. For one thing, I'm going to enter this f of y function in my y equals, only I can't really use y in here. I'm going to use x instead. I'm going to call this x squared plus 1. And it'll be okay using x's instead of y's. You'll see, as long as we do our integral function with dx instead of dy, this will all work out the way it's supposed to. Next, I'm going to build my a sub 2 function based off of that. So I'm going to write that in y3. That's going to be pi times, open a parentheses, 10 minus, and f of y, so that's going to be alpha trace y2, because that's where I stored f of y, albeit with x's. And then that whole thing needs to be squared. So this y3 now is my a sub 2 of y function. Quitting out of there, let me do my integral, math 9. And that's going to be from 0 to 3. And now I'm going to do alpha trace y3, because that's where I stored a sub y, or a sub 2 of y. And again, I'm going to have to put a dx in here because everything I did in my y equals was in terms of x. So I have to make sure that my differential here matches the dummy variable that I actually used. Pressing enter now, that comes out to 407.150. And that's it for this one. On this no calculator free response problem, I have this R region, and I've got the functions y equals 2x and x squared forming the bounding functions here. First task is to find the area of R. So I'm just going to take an integral from the left to the right side of that bounded region, doing top minus bottom inside the integral. So on the left side, we've got x equals 0, and this goes until we get to x equals 2, that second intersection point, which they pretty much handed to me. So I have the integral then from 0 to 2 of top minus bottom is going to be 2x minus x squared dx. And I'm going to have to do this the old-fashioned way with antiderivatives since I don't have a calculator for this. So that's going to be, let's see here, x squared minus, this bumps up to a 3, so this is 1 over 3 x cubed. So I've got everything here with 2 plugged in, minus all this stuff with 0 plugged in. All that stuff with 0 goes away. I mean, you could actually stop here because it's all constants, but if you want to simplify, all this stuff with 0 just goes away. Over here we've got 4 minus 8 thirds. Well, 4 is really 12 thirds, so 12 thirds minus 8 thirds gives us 4 thirds. For this part, they're telling us region R is the base of a solid, and for this solid at each x, the cross-section perpendicular to the x-axis has area of this a of x function here. We want to find the volume of that solid, so we're just going to integrate this area function from left to right. So we're going to do integral from 0 to 2 to get the volume of a of x dx. So that's going to be sine of pi over 2x dx. Antiderivative of that is going to be, let's see here, that would be negative cosine of pi over 2x divided by the inner derivative of pi over 2. So we're actually multiplying by 2 over pi. So when the dust settles, we have negative 2 over pi cosine of pi over 2x evaluated from 0 to 2. So we've got this stuff with 2 plugged in, and I'll just pull this negative 2 over pi outside now. So we have cosine of pi over 2 times 2 minus cosine of pi over 2 times 0. So this is really cosine of just pi, which is negative 1. So we have a negative 2 over pi out there. We have a negative 1 inside. And this is cosine of 0, which is just 1. But we're subtracting that, so we're doing minus 1 again. So this is really negative 2 times negative 2 over pi. That's going to be positive 4 over pi when all is said and done. For this problem, this part, another solid has the same base r, but this time around, cross-sections perpendicular to the y-axis are squares, right? But don't evaluate an integral for volume of this solid. All right, so we're going to have to rewrite our functions here to talk about kind of the bases of these squares. So this first function I'm going to rewrite. I'm going to basically solve for x on both of these. So I've got x equals y over 2, or 1/2 y. And over here I'm going to have x equals the square root of y. So this is the 1/2 y function. This is the square root of y function now. And this time around, writing the area function out. Now these squares, these bases, so in general, a square has an area of s squared. I'm going to write a of y equals s squared. I'm going to write a sub 2 so I don't confuse this a with the one that I had in the other part of this problem. But now we have to define the side of the square. Since these squares are perpendicular to the y-axis, they're basically going from the left side to the right side of this bounded region. So I need the difference between those two sides. That difference is just going to be the right function minus the left function. So radical y minus 1/2 y. And I'll be squaring all that. So that's my area function for each of these squares as a function of y. To get the volume by chopping this into all those different squares and adding them together, I'm going to write volume equals the integral from, we're going from 0 to 4, because we have to go from bottom to top now, integrating with respect to y. And in here, I'm just going to put a sub 2 of y dy, because I already wrote out all that stuff. And they said, don't evaluate, so I'm not going to evaluate. This is done.